Hello students, in previous class we already discussed about what is kinetic energy or basically energy and different types of energy, and we concentrate on only mechanical energy, and the total type of mechanical energy are divided into two types, that is potential energy and kinetic energy. And we already discussed what is kinetic energy, the energy possessed by a body due to its motion, and the formula for the kinetic energy we already discussed, that is half mv square, where v is what? Speed of the body and mass of the body is m. So kinetic energy possessed by a body of mass m which is moving with speed v is defined as half mv square, and the relation of kinetic energy with linear momentum, that is kinetic energy equal to p square divided by 2m, or else we can write this as the linear momentum equal to 2m into kinetic energy under root. So we already studied about these relations of and expression of kinetic energy and relation between linear momentum and kinetic energy. Then we discussed what is work energy power theorem. So according to work energy power theorem, the total work done on a body equal to the total change in kinetic energy, or this can be expressed as kinetic energy final minus kinetic energy initial. Okay, this is known as the work energy theorem, which is very important, and by the application of this we can solve a large amount of numericals. So what is total work done? The work done by all the forces applied on the body, that is maybe the work done due to external force, or the work done due to any conservative force, or if there is any non-conservative force applied on the body, plus if the body is moved in any non-inertial frame, then if there is any pseudo force present, then also the work done due to the pseudo force. So this is the combination of total work done on the body, which is equivalent to what? The net change in kinetic energy, which is known as work energy theorem. Clear? So from this relation of kinetic energy and relation between kinetic energy and linear momentum, we established that the kinetic energy is directly proportional to the square of speed if mass is constant, and the kinetic energy is also directly proportional to mass if speed is constant. Clear? Here the relation between kinetic energy and speed is in a quadratic equation, and here the relation between kinetic energy and mass is a linear equation. So if we plot the graph of kinetic energy with respect to speed when mass remain constant, the graph will be like this. Okay, here mass is constant. Okay, what if we plot the graph between kinetic energy and mass when speed remain constant? The graph will be like a straight line. Here speed is constant. Okay, so let this be x axis, this will be y axis, and here let this will be x axis and this is y axis. Clear? As here the kinetic energy can be written as some constant k into v square, and here we can write the kinetic energy can be written as some constant k into mass. So this is a linear equation, and this expression will be a equation of parabola. So for if we are taking v along x axis, so for both positive and negative value of x, the value of kinetic energy will be positive, so the graph will be like this. Okay, it is symmetric about the y axis. Clear? You have to remember the graphs. And else if we plot the graph between momentum and kinetic energy by depending on these relations, so if kinetic energy is directly proportional to momentum square if mass remain constant. Similarly, if we plot the graph taking kinetic energy along y axis and linear momentum along x axis, the graph will be again like parabola. Okay, because from this equation we can write the kinetic energy equal to some constant k into p square. So for both positive and negative value of p, the kinetic energy will be positive. So now let us discuss how to derive the work energy theorem. Okay, so derivation of work energy theorem. What is work energy theorem? The total work done equal to net change in kinetic energy, or this can be written as kinetic energy final minus kinetic energy initial. Okay, so let us now derive this relation. How kinetic work energy theorem is derived. So first of all, consider a block of mass m which is placed on a smooth horizontal surface, okay, and initially at t equal to 0 second, the velocity is u and the position, let the point is a and the position x equal to x0, okay, and due to application of an external force F, the block displaced to a further point B, okay, and here the time interval t equal to t second and the velocity of the block is v and its displacement let x equal to x naught. Clear? So due to application of this external force F, the block is displaced from x equal to 0 to x equal to x naught in a given time t second, and initially the velocity of the block is u, and due to application of this force the velocity of the block changes to v. Clear? So due to application of the external force F, let at any instant of time dt the displacement due to the applied force be dx. Okay, at any instant of time dt the block displaces a small displacement of dx. So what will be the amount of work done by this applied force during this small displacement dx? So here we can write the small amount of work done dw due to the small displacement dx will be the dot product of applied force and the displacement dx vector. And as the applied force is applied along this direction, and due to this the displacement of the block dx is also along the same direction as that of the applied force. So angle between the direction of applied force and the direction of displacement is 0. So this can be written as f vector mod into dx vector mod cos of 0 degree, and we know what is cos 0, that is 1. So this will become f ds, which is equivalent to the small amount of work done by displacing the block with a small displacement dx. Okay, but we know that what is f? F can be written as mass of the block into acceleration, or this implies you can write the value f equal to mass or acceleration can be written as dv divided by dt, or the rate of change of velocity, or this implies we can write f equal to mass into dv by dt. So this is the expression of force. Let this equation be 1 and this equation be 2. So now using 2 in 1, we have the small amount of work done dw will be equal to m dv by dt into ds. So now rearranging this, taking ds by dt as a single factor, we will get what? dw will be equal to m into dv into ds by dt. what is ds by dt? ds by dt will be the rate of change of displacement, that is velocity or speed, the magnitude of velocity. So here we can write dw will be equal to mv into dv. So this is the small amount of work done by displacing the block with a small displacement dx. So now we have to find out what is the total amount of work done by the applied force F by displacing the block from x equal to 0 to x equal to x naught. So as here the block is displaced from x equal to 0 to x equal to x naught, and during this displacement the velocity of the block changes from u to v. So by integrating equation 3 to get the total work done, we will get what? Integration of dw from 0 to total work w will be equal to mv dv, and its limit varies from, the velocity varies from x naught, at x equal to 0 the velocity is u, and x equal to x naught, here x naught is the displacement, the velocity is v, so the limit will be u to v. So this implies you can write the total work done w equal to m, integration m is constant, it will be comes out of the integrator factor, it will be v dv from u to v. So this implies we will get what? Total work done w will be equal to m v square by 2, limit varies from u to v. So this implies the total work done w equal to half m, upper limit minus lower limit, v square minus half m u square, or this implies you can add the total work done w equal to, what is half m v square? This is equivalent to the final kinetic energy of the block. So kinetic energy final minus what is half mu square, it is the kinetic energy at the initial position. So this is kinetic energy initial, and this is known as what? This is known as work energy principle, theorem or principle. Okay, so the work energy theorem is proved or derived, the expression is derived, the total work done equal to the net change in kinetic energy or kinetic energy final minus kinetic energy initial. Clear? So here is a question arises, if the net external force acting on a system is 0, then the kinetic energy of the system remain constant. Okay, is it true or false? If the net external force acting on a system is 0, then the kinetic energy of the system remain constant. It is true or false? So as the question asked here, that if the net external force acting on a system is 0, then the kinetic energy of the system remain constant. It is true or false? This statement is not true for each and every case. There is certain exceptional case. So this statement is generally false. When, for example, if here is two charges Q1 and Q2 which are separated by distance r. So this is a system. Clear? So if we allow these charges freely to move, so they can move along this direction due to the internal repulsive force of these two charges. So when initially these two charges are at r distance, after some instant the distance will increase and they will start move along this direction. So initially the kinetic energy of the system is 0, but due to the repulsive force of these two charges, they will gain some kinetic energy. But we are not applying any external force on these two charge system. That's why the initial potential energy stored within these two charges will converted into the kinetic energy. That's why if the net external force acting on a system is 0, then the kinetic energy of the system remain constant is not always true, because in this case the external force applied on the system is 0, but still their kinetic energy changes. So kinetic energy or the internal energy can be converted into the kinetic energy. So if the external force may be 0, but the kinetic energy of the system may or may not remain constant. Okay, so you have to remember this point, that if the total external energy total external force acting on a system is 0, then their kinetic energy may or may not remain constant always. Clear? So this is all about the kinetic energy, the expression of kinetic energy and relation between kinetic and linear momentum, and what is the expression for work energy theorem. Clear? So next we are going to discuss about the potential energy, the second type of mechanical energy, that is known as potential energy. Okay, so what is potential energy? We already discussed about the definition of the potential energy, that this is the mechanical energy which is stored within a body due to its position or change in configuration. What is configuration? Configuration means shape or size. So due to these two changes, the mechanical energy stored within a body due to its position or change in configuration is known as what? Potential energy. Known as potential energy. Okay. Clear? So if the body possesses some energy due to its position with respect to any reference point, then it has certain amount of energy, and that energy is known as potential energy. Or else if the body possesses some energy due to any change in its shape, size or configuration, that is also known as potential energy. So potential energy can be of three types. Number one is gravitational potential energy. Which is basically due to position. Then elastic potential energy, which is basically due to configuration. And there is another type of potential energy which you will study in your second year class, that is electrostatic potential energy. That is the energy stored within a system of charges. If there are two charges Q1 and Q2 placed at a separation of r, then the energy required to make this system will be stored within this system as their potential energy, that is known as electrical potential energy. Okay, but here in this lecture we only discussed about the first two types of potential energy, that is known as gravitational potential energy, which is acquired by the body due to its position, and then elastic potential energy due to the change in configuration of the body, and it is basically regarding a spring. Okay, clear? And what are the example of potential energy that is stored within a body? The examples of potential energy are a block, placed at a height, from ground, a stretched rubber band or spring, okay, or etc. Okay, so if a block is placed, if I am holding this chalk at this position which is at a height, let maybe h from the ground, then this chalk has some energy and this energy stored within this chalk due to its position is known as potential energy. Clear? So the energy stored within a body due to its position or in change in its configuration is known as potential energy. Clear? So first of all we have to discuss about the gravitational potential energy. So gravitational potential energy. So here you have to remember a point. A body can have potential energy if and only if some work is done on the body by a conservative force. Okay, so if we are doing any amount of work on a body by the application of a conservative force only, then that amount of work will be stored within the body as its potential energy. Clear? Because any non-conservative force does not have that ability to store the energy in form of potential energy. Clear? So if the applied force is a conservative force, then only the work done by that applied force will be stored within the body as its potential energy. Clear? So you have to remember this point, that if the work done is done against or work done is done with the application of an conservative force, then that amount of work done will be stored within the body as its potential energy. Clear? So a conservative force is only responsible for potential energy. Clear? So if we are doing any kind of work in a conservative force field, then that work will be stored as potential energy. Clear? So gravitational potential energy is what? If you are performing any kind of work in a gravitational field, then that amount of work will be stored within as what? Gravitational potential energy. So this potential energy basically due to the position. Okay. So let's consider a block of mass m which is placed on the ground, okay, initially at t equal to 0 second. Clear? And we want to displace this block from the ground to a certain height h. Let this initial point be A and the final point be B, and the height of point B from the ground is h. Then the amount of work done to move this block from A to B by the conservative force, here the conservative force is the gravitational force of attraction. which is equal to the weight of the block mg. So mg is the force which is applied by earth on the block to pull it to attract it towards the center of earth, and this type of the force due to the gravitation is a conservative force. So if we are doing some work against this conservative force to bring this block from point A to B, then that amount of work will be stored within the block as its potential energy, and as this potential energy due to the position of the block, that's why it is known as gravitational potential energy. Clear? So our intention is to displace this block from point A to point B, where point A is on the ground level. Let this is at the reference level. Okay, so the ground is considered as the reference level. So the reference level is where we take the potential energy as 0. Clear? So this is the reference level where I am considering the potential energy as 0. It's not bound that this level is always taken as potential energy 0. Maybe I can take this top level as potential energy 0. So any reference level we can assume the potential energy 0 at that reference level. It is up to you. You can choose any reference level as 0 potential energy. So here I am considering the ground level as the reference level where the potential energy is assumed to be 0. So as here the potential energy is assumed to be 0, as the height of the block is from the ground is 0. So now we have to displace this block from A to B by an height h. So what will be the amount of work done by displacing this block? So if the block is attracted by a single force, that is weight of the block towards downward, so to move this block upward we have to apply an external force F along this direction, and we have to apply this force in such a way that the block will move without any acceleration. Okay, so if the block moves upward with acceleration equal to 0 or constant speed, then the applied force F must be equal to the gravitational force mg. Otherwise there will be a net force acting on the block and the block will be start accelerating along the direction. So if we have to move this block without any acceleration or with constant speed, then the value of the applied force must be equal to the value of the weight of the block, that is mg. So if we are considering the work done by the applied force, here the applied force is not a conservative force, but the gravitational force or the weight is a conservative force. So if we are considering the work done by the external agent which is applying the force F, will be considered as if at any instant of time dt the block displaced by displacement dx, and here the direction of displacement is along upward, and also the applied force is acting in upward direction. So the small amount of work done dW by external force will be equal to how much? The amount of external force into the magnitude of the displacement dx into cos of angle between both the displacement and applied force. As both are in upward direction, it will be 0. So the amount of work done dW by the external force is equal to F dx, cos 0 is 1. Clear? So this is the amount of work done by displacing the block with a amount of very small displacement dx by the applied force F. So if you are considering the total amount of work done by displacing the block from height 0 to h, so the total amount of work done will be how much? dW due to external force integration from 0 to W will be equal to, here F is how much, which is equivalent to mg, because the block is moving with 0 acceleration, so I can write m into g into dx. And what is the value of displacement? Limit varies from 0 to capital H. Clear? So by solving this I can write that this implies, by solving I will get the total amount of work done W will be equal to mg integration of dx 0 to h. So this implies it will become the total amount of work done equal to mg into h. Okay, and this is the amount of work done by the external force. This is work done due to the external force, which is equal to mgh. But if we are considering the work done by the gravitational force, which is acting downward, so what will be the expression for the work done? As here the gravitational force mg is acting downward and we are considering the displacement in upward direction. So work done by gravitational force dw amount of work done will be equal to how much? F vector mod dx vector mod cos of angle between the displacement which is upward and the gravitational force which is acting downward, that is 180. So it will be cos of 180. So this implies the small amount of work done by displacing the block with a small displacement dx due to the gravitational force is equal to F dx. Cos 180 is equal to minus 1, so it will be minus F dx. Clear? But we have to find out what? The total work done by displacing the block from A to B. So now integrating this, we will get what? So dw due to the gravitational force limit 0 to w will be equal to how much? Minus F dx integration 0 to h. Here F is how much? Weight of the block, that is mg. So here we can write the total work done due to gravitational force equal to minus mg integration of dx, limit varies from 0 to h. So this implies you will get the work done due to gravitational force is equal to minus mgh. Clear? So from these two relations, here the work done by external force equal to mgh and here the work done by gravitational force equal to minus mgh. Clear? Where gravitational force is a conservative force and here external force is not a conservative force. So here we can write the work done by external force is equal to negative of work done by gravitational force. Okay, work done by external force is equal to the negative of work done by gravitational force, and this amount of work done is stored within the body as gravitational potential energy. Clear? So here we can write so the amount of work done by external force is stored as gravitational potential energy. So the potential energy of the block at point P, let it be denoted by potential energy denoted by capital U at B is equal to how much? mgh. Okay. So the amount of work done by external force is stored within the body as gravitational potential energy, that is equal to UB equal to mgh. Clear? So we can write potential energy U equal to work done by external force or which is equal to negative of work done by conservative force. Okay. So potential energy can be defined as the work done by external force or negative of work done by conservative force. So at a height h from the ground, if ground is considered as the level of zero potential energy, the potential energy stored within the body at a height h will be how much? mgh. Okay. So this is the required expression for gravitational potential energy which will be stored within the body due to its position. You have to remember the expression, that is mgh, where h is the height of the body from the ground. Clear? Where ground is considered as what? Zero gravitational potential energy. If we are taking the reverse case, here I am taking the reference plane. So here potential energy is considered as 0. Then if the block from this position drop to the ground, okay, let this height position be B, this position be A, and the distance between these two positions is H. Now I am considering the reference plane as the top level at a height H, where the potential energy is considered to be 0. Then what will be the value of potential energy at the bottom of the ground when the block is dropped to this point? So in this case, the weight of the block is acting downward, gravitational force mg. So if we want to move this block with 0 acceleration, we have to apply a force in upward direction F, which is magnitude equal to the value of mg, to move the block with 0 acceleration or constant velocity. Then as we know, the potential energy will be equal to the negative of work done by conservative force or equal to the work done by external force. So here the work done by external force will be how much? The external force is applied in upward direction and the body is displaced in downward direction. So by proceeding in previous format, the dW amount of work done by the external force will be how much? F. If we are considering a small displacement during this motion, dx, then it will be F dx cos 180, because in this case the applied force is acting upward and body is displacing downward. So the total work done by the external force will be equal to how much? Minus F dx. Integration of dx vary from 0 to h. So this implies, as the body is moving with 0 acceleration, so applied force is also equal to the gravitational force, that is mg. So total work done by the external force will be equal to minus mg, and dx integration 0 to h will be h. Clear? So this is the amount of work done by external force. Similarly, work done by gravitational force will be equal to how much? In this case, the body is displacing downward and the gravitational force is also acting downward. So the work done will be positive, and which will be equal to mgh. Clear? So work done by gravitational force in this case is positive and external force is negative, and according to the relation, the potential energy stored in the body will be the negative of work done by conservative force or equal to the work done by external force. So here the work done by external force is minus mgh, or if we are considering the negative work done by the conservative force, this is also minus of gravitational force work done, equal to minus mgh. So this will be the amount of potential energy stored within the block at point B. So the potential energy at point B in this case will be how much? Minus mgh. Clear? Where the potential energy is to be 0 at the top point. Clear? This is the expression for gravitational potential energy, which is possessed by a body due to its position. So next we will discuss the potential energy due to change in configuration of a body, or that is known as elastic potential energy. And basically we will considering it as a spring potential energy. Okay, So spring, all of you know, it is a spiral structure like this. If one end of the spring is fixed and initially the length of the spring is L, or this is the natural length of the spring. Okay, so in this position the spring is in relaxed case condition, clear? But if we have stretched this spring by a certain amount, okay, if the spring is get stretched by an amount x, then a restoring force comes to play which always tries to bring back the spring to its natural length, clear? We may stretch the spring by x, or we can also compress the spring by same amount x. So whenever there is any kind of disturbance of the spring from its natural length, whether it gets stretched by certain amount or it gets compressed by certain amount, then a restoring force always acts along the spring which always tries to brought back the spring to its initial length or natural length, clear? And that force is known as spring force or restoring force. For example, if this is the natural length of the spring and I am extending the spring up to a certain amount x, so at this position a restoring force F is acting towards the initial position or natural length, and this force is equal to kx, or in vector form we can write F equal to minus kx, clear? And this is known as, the F is known as restoring force or spring force, okay? And where the k is a constant is known as spring constant, okay? And this spring constant varies from spring to spring. It depends upon the properties of the spring. So the restoring force F is equal to minus kx, or in magnitude which is equal to kx, is known as spring force, and k is known as the spring constant. And from this relation we can write the restoring force F is directly proportional to the displacement, and this law is known as Hooke's law. Okay, we will discuss about broadly in elastic chapter. So the restoring force which always tries to bring back the spring towards its initial position is known as spring force, and this is also a conservative force. Okay, so as this is a conservative force, so this force has the ability to store the work in form of potential energy, and this potential energy stored within the spring is due to its change in shape or size, that is due to change in its configuration. That's why it is known as what? Elastic potential energy. So now we are going to calculate the amount of potential energy stored within the spring due to its change in configuration or shape or size. So let's consider a spring. One end is fixed to a rigid support and a block is attached to it of mass m at other end, and it is moving on a smooth horizontal surface. Okay, at t equal to 0, the displacement of the spring from its natural length is considered as 0. That means this length is known as the natural length of the spring. So here there is no restoring force acting on the spring, as the spring remains as its natural length, clear? But in next case I am applying some external force to displace or disturb the spring or extend the spring by a certain amount x from its natural length. So the block, let the initial position be A. So now the block is displaced to point B from its natural length. Its displacement or extension be considered as x. Clear? So this is the natural length. Initially t equal to 0, the displacement from the natural length is 0, but at t equal to t second, the block is displaced by an amount x and comes to a point B. So at this particular position B, a force due to the extension of spring acts towards the natural length, which always tries to bring back the block towards its initial position, and here I am applying an external force F. So we are applying the applied force in such a way that the block is moving with zero acceleration. That means if the block is moving from point A to point B with zero acceleration, then the applied force must be equal to the value of restoring force at this point. Here the restoring force will be equal to how much? Kx. X is the displacement or elongation and k is the spring constant of this given spring K. Clear? So if we are considering the work done at any instant dt when the block is at a distance L, let the displacement be dl. So at this position we want to calculate the amount of work done by the applied force. So the dw amount of work done will be at a distance L at any instant of time dt. What is the work done? The force acting at this point will be equal to how much? K into L. At any instant of time the extension is L, so the force, restoring force which is acting along this direction will be how much? KL. Or to displace the block with zero acceleration we also have to apply the applied force F, which is equal to same as that of KL. So the work done by the applied force due to this small displacement from L to DL will be how much? So dW equal to F vector dot DL vector, and as this condition the DL displacement is along the same direction as that of applied force. So here we can write dW equal to F vector mod DL vector mod cos of 0. This will be equal to F dl, which is equal to dW due to external force. Okay, so this is the value of F at this instant, that is extension is L, so F will be KL into dl is the amount of work done due to the external applied force. Clear? But the spring is elongated from 0 to total displacement x. So the total work done by extending the spring from 0 to x will be how much? We can get by integrating this relation. So it will be KL dl, where dl varies from 0 to maximum x. So this will be equal to total work done by external force equal to k is constant, integration 0 to x L dl. So this will be how much? The work done by external force equal to k L square by 2, limit varies from 0 to x. So this can be written as the work done by external force will be equal to half k x square. Clear? So this is the amount of work done by the external force. Okay, but if we want to calculate the work done by the restoring force or spring force, so at this condition if we want to calculate the work done by spring force, the spring force will act along this direction towards the mean position and the displacement is along this direction. So the angle between displacement and spring force is 180 degree. So the dW amount of work done at that instant due to spring force will be equal to F spring force dot dl integration. So this will be work done due to spring force equal to K L dl, and angle between the spring force and displacement is 180, so it will be cos of 180. Limit varies from 0 to x. Clear? So by integrating this we will get what? The total work done by spring force is equal to minus half kx square. Okay, so this is the amount of work done by spring force. So work done by external force is equal to negative of work done by spring force, and as we know, the work done by external force is equal to the amount of potential energy stored within the body, or as we discussed, the potential energy is equal to work done by external force or the negative of work done by conservative force. So here the potential energy at B will be equal to work done by external force is how much? Half kx square, or if we are considering the negative of work done by conservative force, our spring force is a conservative force. So negative of work done by conservative force, that is minus of minus half kx square. Clear? So the potential energy stored within the spring at position B due to an elongation of x is how much? Half kx square, where x is the elongation of the spring. So this is the expression for potential energy stored within a spring due to change in its size, shape or configuration. That's why this potential energy is known as what? Elastic potential energy. And here x is what? Elongation or compression, both. From equilibrium position or natural length. Clear? And k is known as spring constant. Okay, so this is all about your expression for potential energy stored within a spring due to its change in configuration. Okay, so next we will discuss further. Thank you.